Hello students, good evening. So we are in the session 6 of work, energy and power topic. So we are in the discussion of applications of the work energy theorem. Correct. Even in the session 5, right? What we were doing, we were actually doing the applications of the work energy theorem with regard to the kinematics related systems. Means, see, what do we mean by kinematics related systems? We are talking about the objects moving across the pulley or on an inclined plane, on a horizontal plane. That is what we are considering as what the kinematics related systems. So we'll have to cover the model of question including friction, because the question that we solved in the session 5, right, we were assuming that the surface are what frictionless. So here we'll look at a question which is involving friction. Then we will go into the next category of applications of the work energy theorem. Okay. So look at this one. An object is given initial velocity of 60 meter per second along an inclined plane of 30 degrees. So look at the inclined plane. What is the inclined plane? Here we have the angle of the inclined plane is what, 30. The object is given an initial velocity 60 meter per second along the inclined plane. Means we are assuming it to be moving up. How much distance along the plane will this object travel before stopping? Means as it is going upright, what will happen? The object potential energy will increase. The object potential energy will be increasing. Generally, what do we see? The kinetic energy will decrease, right? Here, they are also mentioning about the friction concept. So they are giving us what? Coefficient of friction between the surfaces is what? 0.1, which means we have to consider there is a friction. Here we have to consider there is a friction. What they are asking? How much distance along the plane will this object travel before stopping? Means let us say it is stopping here. This distance L they are asking. What is the distance covered along the plane before this object is actually stopping? So here what we'll do, we'll consider the starting point as 0.1 and the point where it is coming to rest as what? 0.2. So we'll try to apply the work energy theorem. Okay. So whenever we are applying the work energy theorem, right, we'll be requiring 2 points. Correct. So look at this. What is it that we need to do here? Initially, this object has got kinetic energy. What is the kinetic energy? Here they are not mentioning about the mass. They are not giving us what is the mass of the object. So we have to take it as what? M. M is the mass of the object. Anyway, that will not come in the final answer. Kinetic energy is what? Half into M into V square. V is what? 60. So how much it is? 60 square means what? 3600. 2 ones are 2 1800s. So what do we have? M into 1800. That is what is the kinetic energy at the point 1. What is the potential energy? We will take the bottom point as what? The reference, right? Generally we will take the surface of the earth or the bottommost point like the reference. So we'll take this as a reference line. Means gravitational potential energy of the block will be what? Initially 0, because it is at the reference line. Finally it is ending up at the point 2. Look at this, at point 2, right? What is the kinetic energy? 0, because it is stopping. It is stopping, so kinetic energy will be what? 0. What about the potential energy at point 2? How do we know? When it is traveling a distance L, look at the vertical height gained by the object. Let us say vertical height is h. From the right angle triangle, right, what do we have? Sin 30 is equal to h by L. Means what? H is equal to L into sin 30. What is sin 30? Half. So height gained by is what? L by 2. So what is the potential energy going to be? M into G is what? 10 into L by 2. That is what? M into 5 into L. 10 by 2 is what? 5. That is the potential energy. So we are able to get what is the kinetic energy and what is the potential energy at point 1 and point 2. So here if you look at the block moving along the inclined plane, right, there will be a normal reaction. But remember, since it is moving along the inclined plane, what will be the work done by normal reaction? 0. Work done by the, because any object moving along the inclined plane, right, work done by the normal reaction will be what? 0, correct? Then there will be, of course, the friction. So look at it. The block is moving up the plane. So friction will be acting what? Opposite direction. If the block is moving upwards the plane, friction is going to act downwards the plane, correct? So what we'll do is we'll just erase this space and write down the things that we are already getting. What are we already having in our hand? So look at what is there with us. Kinetic energy at point 1 is there. KE1, that is how much? M into 1800. We also have potential energy at point 1, that is 0. Then we have kinetic energy at point 2, that is 0. What about the potential energy at point 2? M into 5 into L. Let us keep them. Now we'll erase this space so that we can get the calculation about work done by friction, because normal reaction is not doing work. Then there is a friction. So what are the total forces acting on that block? There is gravity, which is already coming in the potential energy term. And then there is the normal reaction and there is a friction. So look at this. If you consider the object which is on the inclined plane, right, remember mg cos theta will be the component of the weight perpendicular to the plane. Perpendicular to plane, there is no motion, right? Motion is along the plane. So we will get normal reaction value. What is it? M into g is 10. Theta is what? 30, right? So cos 30 is what? Root 3 by 2. So that is what? So M into 5 into root 3. That is our normal reaction. Okay. Then the friction force will be what? Since there is a motion here, we will consider the friction to be what? Kinetic friction. They are not mentioned, but we will have to consider it to what? Kinetic friction. So this is what? Coefficient of kinetic friction. Friction force is what? Coefficient of kinetic friction into normal reaction, right? Which is what? M into 5 into root 3. So this is M into 0.1 into 5 is what? 0.5 root 3. That is what is the frictional force. Now work done by frictional force. Look at this. The displacement along the plane is what? L. Frictional force is along the plane downwards. So work done by friction, right, will be what? Frictional force into the displacement into cos 180. Why cos 180? Because they are in opposite direction. So it will be what? Negative. Cos 180 is what? Minus 1. So look at this. Minus M into 0.5 root 3 into L. That is the work done by the frictional force. So what is the work done by the frictional force? Minus M into 0.5 root 3 into L. That is the work done by the frictional force. Okay. Now the thing is what? The work done by the non-conservative forces and other external forces. That is the work energy theorem statement, right? Work done by non-conservative forces and other external forces is equal to what? Change in kinetic energy plus change in potential energy. That is what we have to apply, right? That is the work energy theorem statement. Now here, when you apply the work energy theorem statement, right, what do we have? Work done by non-conservative forces and other external forces. There is only one, that is the friction. That is equal to what? Change in kinetic energy, means final kinetic energy 0 minus initial. So 0 minus M into 1800 plus change in potential energy means what? Final potential energy minus initial. That is what? M into 5L minus 0. Okay. So here we can see that M is going to get cancelled on both sides. Minus 0.5 root 3L is equal to what? Minus 1800 plus 5L. So we'll have to rearrange the number 1800 will come to the left side. That is equal to what? 5 plus 0.5 root 3 into L. Okay, what is it? The L value from here will be what? 1800 by 5 plus 0.5 root 3. That is what is the distance that is covered by the object along the plane before it is stopping. So here if you want the answer in terms of the actual decimal value or something, we can substitute the root 3 as what? 1.732, and we can do the simplification. We can substitute the value of root 3 as what? 1.732 and then do the simplification part. Then we will be able to get what is the exact answer. Check it, guys. So what is the, so in this kind of question, right, when there is a friction means obviously there is a work done by the non-conservative forces, right? So that term will come. Here we will not be able to use conservation of mechanical energy. In these kind of questions we will not be able to use what? Conservation of mechanical energy. That we cannot use. Okay. So guys, you can confirm whether you are also able to get the same answer or not. So what is the value of L we must get? L will be what? 1800 divided by 5 plus 0.5 into root 3. Okay. Let us move on to the next category. Next category is the applications of the work energy theorem concept in problems involving the spring force. Remember, with regard to spring, already we talked about it, right? If there is a spring in the natural length, what is the spring potential energy? 0. When the spring is either expanded by a value x or compressed by a value x, then the potential energy of the spring will be what? Half k times x square. K is what? The stiffness constant. We also call it as what? The spring constant. Okay. So what do we call the K as? Stiffness constant or the spring constant. Okay. So here in our discussions, right, we will consider that the springs are what? Massless. Remember in the Newton's laws of motion, right, when we talked about the pulley, okay, so or the rope, we were generally making the assumption that the pulley or the rope will be massless. So here, you know, the spring we will consider it as massless. Because of this, what happens is, now keep this in mind carefully, when the spring is getting expanded or compressed, we might be thinking that, okay, can the spring have a kinetic energy? Spring will not have any kinetic energy. Why? Because our assumption is spring is massless. Kinetic energy will come only when the body is having mass, right? So for a spring, we will be just having what? Spring potential energy. Similarly, in some cases, spring may be elongating vertical direction or getting compressed. There also we might think, what about, because our normal understanding is what? You take a spring in hand, it will have mass. That is what we assume, right? So when the spring is coming down, right, then we will start thinking about the gravitational potential energy. Or when the spring is going up in terms of vertical distance, we will start thinking about what? Gravitational potential energy. But in most of the problems we solve, we will not consider the kinetic energy part as well as the gravitational potential energy of that spring. Why? Because spring is in our case massless. But particularly when it comes to questions at the JEE advanced level, you may even be given some questions where the spring itself can be having a mass. So we'll see some, you know, miscellaneous questions in the end of the chapter where we can have the spring having a mass. Okay, so we'll deal with some questions later, but this is about the general kind of problems we have where we are going to have the spring potential energy coming into the work energy theorem problems. Okay, so we'll start with very basic question, then we'll go on to the real application level problems. Look at this. A spring of constant 800 Newton per meter has an extension of 5 centimeter. Means initially itself, right, the spring is extended by how much? 5 centimeter. Means initially it will have spring potential energy. What is the value? Can you tell me? Half into K is what? 800 into, remember this is in centimeter. 5 centimeter means what? 5 by 100, right? Which is what? 1 by 20 meter. So half kx square, right? That is what? 2 ones are 2 400s. 400 into 1 by 20 square means what? 20 into 20. That is also 400. Cancel. The energy will be coming in terms of SI unit. So what is the initial spring potential energy? 1 joule. Okay. The work done in extending the spring from 5 centimeter to 15 centimeter. So initial extension is what? 5 centimeter. They are asking if you are extending it from here to 15 centimeter. Look at what is the final spring potential energy. Half into K is 800 into x square. Here final state, what is the elongation? 15 centimeter means 15 by 100, that is 3 by 20 meter. So we will get what? 3 by 20 the square, that is what? Again 400 into 9 by 400, that is what? 9 joules. So spring initially it is having a potential energy of how much? 1 joule. Finally what is the potential energy? 9 joules. They are asking what is the work done. Remember, work energy theorem concept is what? Work done by the external forces, because we are applying the external force to elongate the spring, right? Work done by the external forces and other non-conservative forces, that is the work energy theorem statement, right? Will be equal to what? Change in kinetic energy plus change in potential energy, because there is only spring here. Already we said we'll assume spring massless. So for spring only one energy term will come. What is it? Spring potential energy. So we'll have change in the potential energy, because only for the spring, right, it does not have a mass. So kinetic energy of the spring will not have any meaning. So what is the change in spring potential energy? Means final value, which is 9 joules, minus initial value 1 joule. What is it? 9 minus 1, that is what? 8 joules. So what is the answer for this question? The work done in extending the spring from the initial state of 5 centimeter extension to that 15 centimeter, right? What is the work done in this case? 8 joules it will come. Okay. So we'll move on to the next question. This is an interesting situation, because we'll talk about this kind of situation for the spring even when we go to the oscillations chapter, because in oscillations also we are going to talk about the spring connected to a mass. Okay, an object of mass m is attached to a vertical spring. What is the constant for the spring? K, and is allowed to fall under gravity. Means we are attaching an object of mass m to the spring of constant K, and we are allowing it to fall. When this falling means what is going to happen? The mass is going to come down and the spring is going to get elongated. The mass will be coming down, the spring is going to get what? Elongated. Okay, what is the distance traversed by the object before it being stopped? We need to find what? From the starting point, this starting point, it will keep coming down, right? We have to find what is the distance that is covered by the object before it is coming to rest. So look at this interesting thing. Initially we are releasing the object from rest only, right? We are allowing it to fall under gravity. It is coming down, and finally also it is what? At rest. How this is going to happen? See, when you are releasing a mass attached to a spring, look at this visualization here. So from here we are releasing it. When you release it, right, look at this, it is going down. As it is going down, you know what happens? the spring will develop the restoring force. As it is going down, the spring will be developing what? Restoring force. Okay. What is the restoring force related to the extension of the spring? Correct. Now you will reach a stage. You will reach a stage where the restoring force, right? The restoring force is able to balance the weight of the object. You will reach a stage once you leave the block from the top, right? You will reach a stage where the restoring force in the spring will be able to balance the weight. That is what in oscillations language, right, we will call it as equilibrium point. So what do we call that as? Equilibrium point. But the body will not stop here. Why? You know why the body will not stop here? Because since the body is coming from the top, it would have already gained some velocity. It will be gaining some velocity, right? So from the equilibrium point, it will keep going to the other side. Now when it is going to other side, remember what is going to happen? The spring force value, right, will be more than the gravity, because equilibrium means spring force is balancing weight. If you elongate the spring more, means what is going to happen? The spring force will be higher. So while it is going away from the equilibrium, it is going down away from the equilibrium, right? There will be a net force acting on that mass towards the equilibrium. So look at what is this happening here. When the object is going further down, there will be a net force acting on that object upwards. Okay, this is the reason for the oscillations to happen. So for oscillations to happen, right, whenever an object is moving away from the equilibrium position, there must be a net force acting on it towards the equilibrium. Then only the oscillations will continue. So we'll talk about it when we go to oscillations. What is it? For the oscillations to occur, when an object is moving away from equilibrium, when an object is moving away from equilibrium, there must be a net force acting towards the equilibrium point. Okay, so that force is the force that will keep the oscillations going. Okay, so this is an important thing. We'll again talk about it when we go to the waves and oscillation chapter. Okay, but look at this. Now this will have a net force upwards when it is going further down from the equilibrium position. So means what? This object will be now under retardation. So its velocity keep decreasing till it reaches the point on this side. So this point is generally what we call as the extreme position. So in oscillations, these points will be important. Extreme position, like you have extreme position, then there will be equilibrium. So for the equilibrium, right, on one side you will have extreme position 1, other side you will have the extreme position 2. You can see here, this is like what? Extreme position 1, this is like extreme position 2. So this object is going to perform what? This object is essentially going to perform oscillations. The object is going to perform what? Oscillations. But here the question is not about oscillations. We are just trying to understand what is happening with regard to this object. Again, we'll discuss about these kind of things when we go to oscillation chapter. But here, what is our task? Our task is we need to find what is the distance that is traversed by the object before it is being stopped. Okay, so look at it. When it is stopped at this point, maybe I'll draw a parallel diagram so that we can see. Okay, so this is the final point where it is stopping. Okay, this is the final point. Let us call it as 2. This is the initial point. Let us call it as 1. Okay, look at this. What is the kinetic energy here? For the spring, there will be spring potential energy. For this object, right, there will be gravitational potential energy involved because it is moving vertically, and of course the kinetic energy. Point 1, what is the kinetic energy of the object? We are releasing it, right? Means kinetic energy is 0. Point 2, again it is coming to rest. So kinetic energy will be 0. Point 1 kinetic energy 0, point 2 also kinetic energy 0. When we release it, velocity 0. Finally, you can see here also the velocity is what, 0, right? What about the spring potential energy initially? Initially when we release, the spring is in the natural state. So that is 0. Spring potential energy in the final state. So if from here the extension of the spring is x, what is the spring potential energy? Half into k into the x square. Correct. Now initially, what is the gravitational potential energy of the mass? See, for gravitational potential energy, what we need to have? We need to have a reference, right? Without reference, we cannot talk about the gravitational potential energy. So for that, what we'll do is the bottommost point, that is general thing, right? Bottommost point will be our reference. Means the gravitational potential energy at point 2 will be what? 0. For the mass m at the point 2, final point, what is the gravitational potential energy? 0. That is what is our reference. Look at initial point. Initial point is at a vertical height x from the reference. So initial gravitational potential energy of the mass is what? Mg into x. Now here we are going to neglect the air resistance. Air resistance and all we will neglect. So look at this. If you consider the spring and the mass together, that is what we will also technically call as a system, like that we will say. So we are considering the spring and the mass together. For this, right, there is no air resistance, means there will be no work done by the external forces or other non-conservative forces. Means what? We can apply the conservation of mechanical energy. So we can see here, when we talk about the conservation of mechanical energy, here we are getting what? Both spring potential energy term involved as well as the gravitational potential energy. But the given situation, right, initial point kinetic energy of the object is what? 0. Final point also it is 0. So look at this, ke1 plus pe spring plus pe gravitational, total value is what? mgx, that is equal to ke2 plus potential energy of the spring in the second condition plus gravitational potential energy. So look at this, what we'll have? 1x we can cancel it off. Then what we'll have? 2mg is equal to kx. That means 2mg by k, that is x. What is x value? 2mg by k. So when you release it, right, it will go how much distance below from the starting point? It will go to a distance of what? 2mg by k. That much distance it will go below before it is again coming to rest. Okay. Look at this one. A block of mass m is moving on a smooth horizontal floor. Means what? There is no friction. With a constant velocity v0. Collides with a light spring. So generally these words, right, light means what? So even if they are not mentioning, we will generally assume the spring to be massless. Okay. Light spring means what? No mass. It collides with a light spring of stiffness constant k, which is rigidly fixed in the horizontal position with a vertical wall. Find maximum compression in the spring. So look at the situation. We are having a block. It is moving with a constant velocity v0, coming and colliding with the spring. After that, what is going to happen? It is coming and colliding with the spring. It will start compressing the spring. Look at this. It will start compressing the spring. They are asking what is the maximum compression in the spring. Maximum compression means what? The block will keep compressing it. When the block is compressing, what is going to happen? The potential energy of the spring will be increasing. Kinetic energy of the block will be decreasing. Maximum compression means what? When we will say maximum compression, the block velocity must become 0. That is it, right? Because the block is not able to compress the spring anymore. That is what you will consider as the maximum compression case. Means at this point B, So maybe you can take as the initial point as what A, and this maximum compression is what, point B. At point B, the velocity will become 0. That means kinetic energy at the point B is what, 0. If the spring is compressed by value x, then the spring potential energy at the point B is what, half kx square. Okay, now look at this. The block is moving on the horizontal surface. So when it is moving on the horizontal surface, right, that is what you will take as the reference. So since it is moving always along the horizontal surface, there will be no change in terms of the gravitational potential energy. That is always 0, because at point A also it is on that same horizontal level. Point B also it is the same horizontal level. So we don't need to consider the gravitational potential energy. Other than this, what else is there? Friction is not there. Normal reaction will be there. But since it is moving along the surface, work done by normal reaction is what, 0. Since the block is moving along the contact surface, work done by normal reaction is what, 0. Then at the starting point A, what is the kinetic energy of the mass? Half into m into v naught square. The velocity there is what, v naught they are saying. Okay, and at the point A, what is the spring potential energy? Spring is in the natural state, right? That will be 0. Since there is no work done by non-conservative forces and other external forces, what we can have here? We can have the conservation of mechanical energy. Okay, so we are again considering the spring and the mass together, like we call it as what, one system. For this, when you apply conservation of mechanical energy, what we'll have? We'll be having, what do we have? Initial starting point A, kinetic energy plus spring potential energy. Here, why the gravitational potential energy of the mass m is not coming into picture? Because it is always moving along the reference line, so it is always 0. So initially kinetic energy is what, half m v naught square, potential energy anyway 0, is equal to the kinetic energy plus potential energy final state. Kinetic energy 0, potential energy is there, half kx square. Half is cancelled, so m v naught square by k, that is x square. So from here x is what, root m v naught square by k. So that is the maximum compression. So here we are solving the question by using some parameters. Sometimes we can even have questions by using numbers, like they can tell the spring constant is this much, mass of the block is this much, its initial velocity is so and so. When you have the values, means those values as it is will go into that expression. What is the maximum compression of the spring here? X will be equal to what, root m v naught square by k. Okay, so this is another model of question that we can have. Look at this. In fact, this is a question that has come in one of the previous year JEE mains. Okay, the block of mass m moving on the frictionless horizontal surface. Here also there is no friction. There is no friction here. Okay, collides with a spring constant k and compresses it by a length L. Means this is what is our maximum compression. So when the block is colliding and then compressing it, that is L is what, the maximum compression. Here they are asking something different. The maximum momentum of the block after the collision is how much? They are asking us what? See here, they have not given us what is the velocity of the initial velocity of the block. They have not given. When it is just coming and colliding, they have not given us what is the initial velocity. Okay, but what they are asking, the maximum momentum of the block after collision. See, look at this now. When you take the situation where the block is just colliding the spring, look at situation where the block is just colliding the spring. After this, what is going to happen? The velocity of the block keeps decreasing, right? Because when the block is compressing the spring, means spring potential energy will increase, and the block velocity will decrease, kinetic energy also will decrease. Correct? Momentum maximum they are asking. See, when momentum will be maximum, because momentum is what? M into velocity, right? So momentum will be maximum when velocity is maximum. When the velocity of the block will be maximum? At the point of collision. So if you consider the point where it is colliding as the initial point, this is the initial point, right? That is where the momentum is going to be maximum. For the block, that is where the momentum is going to be maximum. So we need to find what is that momentum value. We need to find what is the momentum. Okay. So see how we can approach it. So what do we need to do? Again, this question, right? Most of it is like our previous problem only. Work done by normal reaction is 0, no friction. So we can use conservation of mechanical energy principle. And here for the block, let us say V is the velocity at the time of collision. Then kinetic energy, let us call it as 0.1, is what? Half mv square. Spring potential energy 0. Here also the gravitational potential energy concept will not come. Why? Because the block is moving. This line we will take as what? The reference. Since it is always moving along the reference, gravitational potential energy of the block will be what? 0. Gravitational potential energy of the block is what? 0. Okay. Now, when the spring is fully compressed, the maximum compression state, right? That is our state 2. What is the kinetic energy of the block? 0. What is the spring potential energy? Half into K into L square, because they are giving us the block is compressing the spring by value L. Okay. So when we apply the conservation of mechanical energy, what do we have? We'll have that initially at the time of collision, the kinetic energy plus potential energy, which is just half mv square, that is equal to what? Final kinetic energy plus potential energy, that is half kl square. So here half is cancelled. So from here v square is equal to what? kl square by m. So okay, so from here we will be able to find v. What will be v value? We have to take a square root on both sides. That's it. No. How do we get the v value? Take a square root on both sides. So v will come to us. V will be equal to what? Root of kl square by m. That is what? Maybe we can say root k by m into l. That l only will come out because it is l square, right? But they are not asking us the velocity. They are asking us what? The maximum momentum. This is the initial velocity rate. That is what is the maximum value of the velocity for the block. The corresponding momentum there will be the maximum momentum. The corresponding momentum there will be what? Maximum momentum. So what is the value going to be? Mass times velocity, which is what? Mass times root k by m into l. So m we can take it inside. It will become what? M square. Root m into k, l is outside. That is what? That is our maximum momentum. So look at this. Where is the answer? Root m into k, l will be outside the root. Okay. Clear, guys? See, if you are little bit familiar with this application of the work energy theorem, right? You probably will not do all these. You don't need to do all these step by step. If you are a little bit comfortable, you get the command. So when you will get the command, once you solve certain number of problems, you will get the command over these model of questions. Then you will be able to do things fast. So without, because when you are solving by yourself, right, you will not be obviously giving all these details because you are not solving in a board exam like that. So you will be able to quickly put down the steps and then get the answer. So always, we'll have to, while practicing also, we have to focus on the time factor. So how do we solve the questions in the stipulated time? Like you are getting 2 minutes to solve the question, means how do you solve the question in 2 minutes? That is what you need to think about if it's a JEE mains level question. Okay guys, so we'll move on to the next one. Look at this. This is another interesting one. The figure given below shows smooth curved track which is terminating in a smooth horizontal part. So this is the curved part, fully curved. It is coming like this, and then this is the horizontal part. It is terminating on the smooth horizontal part. Everything is smooth, means frictionless. A spring of spring constant 400 is attached at one end to the wedge, fixed rigidly with the horizontal part. So this is the spring they are talking about. Okay, a 40-gram mass is released from rest at a height of 4.9 meters. From how much height? It is released 4.9 meters on the curved track. So what is going to happen? It is going to keep coming down along the curved track. Okay, find the maximum compression of the spring. So it will keep coming down. When it comes down finally here, it would have attained some velocity. It would have got some velocity rate. Because of this, it will start compressing the spring. Because of this, it will start compressing the spring. Okay, they're asking us what? The maximum compression of the spring. They're asking us what is the maximum compression of the spring. So here what we do is, we can see here, obviously these kind of questions we have to apply the work energy theorem, right? If you look at the block and the spring together, look at the block and the spring together. Initial state here we consider is the point where we are releasing the block from the top. That is our initial state. What is the initial state? We'll consider the point where releasing the block from the top. Releasing means what? KE1 for the block is 0. What about the PE1? So this you take as a reference, means the horizontal flat, that level you take as a reference, means a point 1 is at a height of 4.9 meters, right? So what is the mass? 40 grams. We should convert this into SI unit. So 40 into 10 power minus 3 into G, 9.8, into H is what? 4.9. So this is what? 4 into 10 power minus 2 into 9.8 into 4.9. Let us not try to simplify it here itself. We will try to carry till the final step. Initially, what about the spring? Spring is in the natural state. Okay, so the initial spring potential energy is what? 0. Now finally, when the block is coming and compressing the spring, the block has compressed the spring. That is our final state. Here also, what about the kinetic energy? Because the block will come to rest. Maximum compression means what? The block will be coming to rest, right? It would have compressed the spring and finally would have come to rest. So kinetic energy of the block, final state is also 0. What about the potential energy? So this is the gravitational. What is the gravitational potential? The block is on the reference line, so 0. What about the spring potential energy? Half into K is what? 400 into x square. This x is what we need to find. X is what? The maximum compression. So here if you look at there is no friction anyway. Other than gravity, there will be only normal reaction, correct, on that block. Remember, normal reaction is what? It is a force that will be perpendicular to contact plane. And the block is moving along the contact plane. So work done by normal reaction is what? 0. Means here also we can apply the condition of what? Conservation of total mechanical energy. Why? Because the work done by the external forces and non-conservative forces is what? 0. So we can apply what? Conservation of mechanical energy. Means initially what is the total mechanical energy? This is 0, this is 0. So only the gravitational potential energy. What is it? 4 into 10 power minus 2 into 9.8 into 4.9. That is equal to final. Final is what? Kinetic energy 0. Gravitation potential 0. Only this will be there. Half into 400 into x square. Okay, so what is half into 400 means we can take it as what? 200. So now it's just a matter of simplification. You can probably tell me what is the answer you are getting. So if you're doing along with me means you would have got the answer by now. Check it guys, what is the answer you are getting? What we will have to do here, just the simplification part, last step. What is it? Left hand side we have 4 into 10 power minus 2 into 9.8 into 4. That is equal to what? 200x square. Bring the 200 to the left side. Okay, this is what? 200s, 2 2's, x square. So we'll have to take a root on both sides. Root of 2 into 4.9 is what? 9.8. So we'll have two 9.8s. 10 power minus 2 is there in the numerator. Denominator 100. Total it will be what? 10 power minus 4. That is our x. So what is it? Two 9.8s are there inside the root. So one 9.8 will come. So remember here everything we are converting into the SI system. So x will be coming in terms of what? Meters. X will be coming in terms of what? Meters. So 9.8. Root 10 power minus 4 is what? 10 power minus 2. So what is the x value? 9.8 into 10 power minus 2 meters. We can also say it as what? 9.8 centimeter. Because what is 10 power minus 2 meter means centimeter only, right? So we can also say it as what? 9.8 centimeters. Okay guys, so this is what is the maximum compression in the spring. Now look at this, finding the maximum compression in the spring with a rough surface. So previously the problems we solved, right? All the problems we were assuming what? The surface is what? Smooth. So here what we will do is we will take up one situation like this. Okay, so we have a spring. This is what? Rough surface. Here it is what? Smooth. So just the block is coming. From the time of colliding with the spring, the roughness is starting. So the mass of the block is m. It is coming with a velocity v0. So there is a coefficient of friction mu and spring constant k. In this question they are asking what? The maximum compression in the spring. In this question what they are asking? The maximum compression value of the spring. That is what they are asking. So how do we proceed? Here the only difference from the previous problem is what? Look at this. Initial state is the point of the block colliding with the spring. So kinetic energy of the block is what? Half into m into v0 square. Here the block is moving on the horizontal line, which we will take as what? The reference. So the gravitational potential energy will not be changing. The gravitational potential energy value will not be changing. Okay, so hence we don't need to consider the gravitational potential energy. Initially spring potential energy 0, because spring is assumed as what? In the natural state. When it is compressing by a value x, final kinetic energy of the block is what? 0. Maximum compression means, the block will come to rest. Final spring potential energy is what? Half into k into x square. What is the final spring potential energy? Half into k into x square, right? Because it is compressed by value x means spring potential energy is what? Half kx square. Now here work done by normal reaction will be 0. Why? Because the block is moving along the plane. Normal reaction is perpendicular. That is okay. But here we will have a work done by friction. So look at this. When the block is moving towards the right side, frictional force will be left. Okay, what about the frictional force value? Remember when we do the vertical balance, right? The block is moving horizontal. You do the vertical balance, we will get normal reaction is what? Mg. So frictional force will be what? Mu into normal reaction, because there is motion means we will have to take it as what? The kinetic friction. If the block is moving to the right side by a value x, displacement is what? X to the right side. So work done by the friction will be what? Force mu mg into x into what is the cos theta value here? What is the cos theta? The angle between them is what? 180. Friction is to the left, body is moving to the right. That's why we'll get what? Cos 180 minus 1 will come. So work done by frictional force is what? Minus mu mgx. What is the work done by friction force? It is what? Minus mu mgx. Okay. So here we are having work done by the non-conservative forces. Then what is the expression we'll be having? What is the expression we'll have? The work energy theorem. Work done by the non-conservative forces and other external forces. What is it? Minus mu mgx. That is equal to what? Change in kinetic energy. Finally 0, initially is 0 minus half m v naught square plus change in potential energy. Finally we have the spring potential energy half kx square. Initially what is it? 0. So finally half kx square minus 0. So look at this, what we'll have? Minus mu mgx is equal to what? Half kx square minus half m v naught square. So here we are not going to solve the question fully. Why? Because in this situation, right, what you will be getting? You will be getting a quadratic equation in terms of x. We will not get, in the previous case what we had, a linear equation. We were able to straight away get what is the value of x, but here it is not like that. Here what we will get is a quadratic equation. I mean, we can solve this equation by the parameters also, but you just remember up to this step. If they give this kind of question with the actual numerical values, means in all these parameter places we will get the values. They will give us mu as say maybe 0.1 or 0.2, so that will come. They will give the mass of the block is what? Some 10 grams, 20 grams, the mass will come. But no, you have to be careful about the units. G value also they will give, K they will give, V naught they will give us. So when you substitute all the values, right, you will be getting a proper quadratic. You will be getting a proper quadratic equation. When you solve the quadratic, you are going to get two roots. This is sometimes important in physics, right? Even in the previous chapters also we saw there will be some boundary conditions for us. What do you mean by boundary condition? Here we are talking about the x as the amount of compression. If in the two roots one of them is negative, other is positive, we will not take the negative value. We would not be taking the negative value. What is the value we will take? We will take the positive value. Okay. So like that we will have to use some boundary conditions. So even in some of the kinematics problems when we solved, right, what is it that we got while solving for the value of time in a quadratic equation? If you are getting one of the root as positive, one is negative, remember what we said? We said time cannot be negative, so take only the positive value, like that. Okay. So this is how you will have to approach the questions where we are having the block compressing a spring on a rough surface. Means here we will be having the friction coming into picture. Okay, so in the work energy theorem statement we will have to include what? The work done by the frictional force. Okay. So look at this one. This is another situation where we have spring on an inclined surface. So all this time we were looking at a spring which is kept horizontal, but a spring can be kept on the inclined surface also. Okay, so how we can have that kind of problems? So here I'm going to discuss about what is the general model of question. We are not taking the specific values. We will just try to solve the different cases by using some parameters. We'll try to solve the cases by using what? Parameters. So look at this. Imagine we have a spring. Okay. To this there is a mass attached. We release it. When you release it, what is going to happen? The block is going to move along the inclined plane down. Then the spring is going to get extended. So in this case they can ask us what is the maximum elongation in the spring. So here the surface can be smooth or surface can be having friction. both kind of questions we should be ready. The surface can be smooth, the surface can be having friction. Okay, so first we will start with the surface as smooth. First we'll start with surface as what? Smooth. Okay, so look at this. When you release it, right, that is our initial point. The block is going to come along the surface, say it is covering a distance L. The angle of the plane is theta. H will be what? Remember what we done. What is it? H by L will be sine theta. So H will be what? L sine theta. So if you take the final point as the reference, this is the point 2 as the reference line for the gravitational potential energy. Okay, so PE2 gravitation is what? 0. What about PE1 gravitation? We're talking about the potential energy of the mass m. What is it? It is at a height h above the reference. M into G into H is what? L sine theta. So usually they will give us the theta value. They will be giving us the theta value. Okay. Now spring. If the block is coming along the plane by value x, L, spring is also elongated by same value, right? If the block is coming along the plane by a value L, spring will also have the same extension, right? So spring potential energy is what? Final state? Half k L square. Initially, spring will be in the natural state. That is our assumption. So potential energy is what? 0. Initially, we are releasing. Means kinetic energy of the block will be what? 0. Finally, also the block will come to rest. So kinetic energy will be 0. If we assume that there is no friction, in this case, if we assume there is no friction, right? Anyway, work done by normal reaction of the block is what? 0. Why? Because normal reaction is perpendicular to the plane and block is moving along the plane. Angle is 90 between them. So again, what we will have? Conservation of mechanical energy means finally the potential energy values plus kinetic energy values. So look at this, point 2, potential energy is 0. Spring potential energy half KL square. Kinetic energy final 0 is equal to initially starting point. What is the gravitational potential energy? mg L sine theta. Initially, what is spring potential energy? 0. Initially, what is the kinetic energy? 0. So from here, we will be able to find what is the value of L. You can see 1 L we can cancel. So from here, what is the value of L coming as? 2 mg sine theta by k. You can see one interesting thing. In the first problem, right, where we have kept the spring vertical and released it. Remember the value of extension before the block is stopped. What is the value we got? 2 mg by k we got. Here what are we getting? 2 mg sine theta by k. Okay, so this is about the spring on the inclined surface. So here the difference will be what? Whatever the distance traveled by the block will be the, in this case it is like what? The spring is getting elongated. In some other cases the spring may be getting compressed also. It depends upon the situation. But when it comes to the gravitational potential energy of the block, we have to be clear that we need to understand what is the vertical separation between the initial point and final point. We have to understand what is the vertical separation. Okay, this thing we have to be careful. So this is about the spring on the inclined surface. See, we are trying to spend some time to go through all the different possible scenarios, so that whenever you look at a problem, right, the more problems you solve, the more familiarity you will have. Okay, and more ideas. So more ideas you collect, right, you will be that much more confident when it comes to solving problems in physics. That is the trick. Okay, so this is about what? Spring on the inclined surface without friction. The previous case is what? Without friction. Now what if we are including friction? What if we are including friction? What will happen? If you include the friction, means not much difference, right? We already solved. Same, let's take the same question. Okay, The block is here, spring constant K. It is moving down. Now look at it. This is the initial point. Final point, it will come to rest. Everything else will be same, right? So I'm just rewriting all the things. PE2 of the spring is what? Half KL square. Okay. KE2 will be 0. PE2 gravitation is 0 because this is what we have taken as the reference. See, all these values we already got. PE1 of the spring is 0. KE1 is 0. PE1 gravitation, remember what is it? MGL sine theta. So everything we did before only, same situation. But only thing is what? When the block is moving along the plane, there is a friction. So remember guys, when the block is moving down the plane, right? When the block is moving down the plane, how the friction is going to act? Opposite direction. And by the way, what will be the frictional force value? Remember, the component of weight perpendicular to the plane is what? Mg cos theta. See, what you studied in Newton's laws of motion, you should keep in touch. It's not like, we have just done it and we forget. So remember, a block on the inclined plane, we will resolve the weight into components, right? Mg sin theta will be along the plane. Mg cos theta will be what? Perpendicular to plane. Since the object is moving along the plane, perpendicular to plane, no motion, means force balance. Normal reaction is what? Mg cos theta. Why are we doing normal reaction? Because we have to give the expression for the friction. Since there is a motion, this is what? Kinetic friction. What is it? Mu into normal reaction. That is the frictional force. The object is coming along the plane down by a value L. That is what you are taking, right? It is moving down by a value L. Friction is what? Opposite. Angle between them is what? 180. So work done by frictional force is what? Mu mg cos theta, which is the force, into displacement L into cos 180 will come. So what is it? Minus. So now that we got the expression, we will just erase all this part. So what is the work done by the frictional force? Minus mu mg cos theta into L. Work done by the non-conservative forces and other external forces is equal to what? Change in kinetic energy. Initially kinetic energy 0, final also 0. Plus change in potential energy, means here we'll have what? Two potential energy terms. Look at this. Spring potential energy. Change means what? Final minus initial. Half KL square minus 0 means half KL square. Plus change in the gravitational potential energy. What is it? Final gravitation is 0. Initial gravitation is what? MGL sin theta. So 0 minus MGL sin theta. What is it? Minus MGL sin theta. So we'll just leave the expression like this. So if we are given the respective numerical values, right, we will be able to substitute and solve and get the answer. Like they will give us what is the mass, they will give us what is the mu value, they will give us what is the the k value. Then here also you can see what are we getting? We are getting a quadratic. So generally whenever there is a friction involved, right, in the case of the block which is compressing the spring on a horizontal surface also, when we took friction, remember when we took friction, right, what we got? We got quadratic. Solving this we will get the roots. Same here also, what are we getting? We are getting a quadratic. You can see there is a quadratic in terms of L. This L is what we are trying to find, right? That's a quadratic equation in terms of L. Solving this we will be able to get two roots. Now we will be able to check if which of them is a negative. That we will have to omit, because we're taking the L as what? The distance by which the mass will move. That cannot be negative, right? So that is the reason why if there is a negative root coming, means we will omit it. Okay, so this is how we will have to look at the applications of the work energy theorem in problems where we are having the frictional force with spring. Okay, so with this we have completed the at least the general level applications of the work energy theorem, including the spring energy concept. Okay, so in the next session, right, we will start with the vertical circular motion. That is an important one. I said, we'll spend some time, we'll do some important derivations in that, and then we'll also look at how the work energy theorem will be applied in terms of understanding the vertical circular motion of an object. Okay, so we'll see in the next class. But no, the crux of the chapter in terms of work energy theorem is over, so you can possibly just start solving problems from whatever you are solving it from the CONCEPTREE material, or you're looking at the past year questions, or whatever the resource you are practicing the problems from. You can go ahead and then start solving the questions, because once we complete this vertical circular motion, the other part will be the system of particles and collision explosion. That is basically what we call as the momentum study part. All this is what this chapter has got two parts. One is the work energy theorem, second part is the momentum study. We will get to the momentum study. Okay, we'll see in the next class.